Good day. For those of you who don't know us, we're the instructional staff for ECE 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we will now extend on recursive problem solving by explicitly solving a number of problems recursively. So, in this topic, we will implement both selection and insertion sort recursively. We will then look at how we can print a binary number where we will also use recursion. We will then implement the binary search algorithm, but we will do so recursively. We will then go on and look at the problem of printing all subsets of a given set of unique objects. Given this, we will then look at how we can determine all appropriate combinations of jumpers given some restrictions. Finally, we will explore the merge sort recursive algorithm. Now, as our first example, let's reinterpret selection sort recursively. Now, you will recall that selection sort, given an array of capacity n, we found the largest entry in the first n entries and copied it or swapped that with the nth entry. We then found the largest entry in the first n-1 entries and swapped that second largest entry with the n-1st entry. We then found the largest in the first n-2 entries and swapped that with the n-2nd entry, and so on and so forth. Therefore, successively, as the for loop iterated, we sorted the list. Let's do this recursively, however. So the base case is if the array has a capacity of 0 or 1. In that case, we're done, so we can just return. However, let's say we have an array of capacity n where n is greater than 1. What we're going to do is we will find the largest entry and swap it with the last entry in the array. Okay? Then we can just call selection sort on the first n-1 entries. Well, let's implement this and we'll discuss it. So here we have the function definition with an empty body. So we will begin by implementing the base case. Well, the base case is straightforward. If the capacity is less than or equal to 1, we just return. So next we have to deal with the recursive case. So in this case, capacity is some value of n greater than 1. Now, you will recall that if we called find max on an array with capacity n, then that returned the index, a value between 0 and n-1 of the largest entry. In this case, we're going to find the maximum entry in the first n-1 entries, and that value is assigned to max index. We will now compare that entry at max index with the last entry of the array of capacity n, which is sitting at index capacity -1. If the largest entry in the first n-1 entries is larger than the last entry, then we will swap the two. Okay, so now we have ensured that the largest entry in an array of capacity n is in the index n-1. Now we have to sort the first n-1 entries. Well, to do that, we will simply call this same function recursively. However, now we are only sorting the first n-1 entries. So consequently, that one will perform the same operation. So how does this sort an array of capacity 4? Well, it finds the largest entry and swaps it with index 3. It then calls recursively selection sort on that array with the second argument being 3. That finds the largest entry in the first 3 entries and swaps that with the third entry, and then recursively calls selection sort with a second argument equal to 2. So now we're only going to sort the first 2 entries. We then find the largest of the 2 entries, swap it with the second one, and then recursively call selection sort on the first entry. Now, if there's only one entry, we are now in the base case, so that returns to the call where the second argument was 2, which is now finished, which returns, and now we are back to the call with the second argument being 3, which is now also finished, which then returns to our call with the second argument being 4, which is also finished, and therefore it returns, and now selection sort has recursively sorted that array of size 4. All right. Let's now reinterpret insertion sort recursively. So, if the array has capacity 0 or 1, as before, we are done. Otherwise, given an array of capacity n greater than 1, what we're going to do now, you'll remember that with insertion sort we have to insert into a sorted array. So let's first recursively sort the first n minus 1 entries, again using insertion sort, and then we will insert the last entry into the now sorted array of n minus 1 entries. All right, straightforward enough. So here is the function body. Here's the base case, as before with selection sort. Now we have to deal with the recursive case. Well, we are going to call insertion sort on the first capacity minus 1 entries. So 1 fewer entries than the number of entries we are trying to sort right now. Now, when insertion sort returns, we're assuming the first capacity minus 1 entries are all sorted, in which case we will now call insert on that array with capacity, and as you will recall, the function we wrote, insert, takes the entry at capacity minus 1 and inserts that into the array starting from 0 going up until capacity minus 2, under the assumption those capacity minus 1 entries are already sorted. Alright, so reasonably straightforward. How does this work on an array of capacity 4? We call insertion sort with a second argument 4. That calls insertion sort on an array of capacity 3, which then calls insertion sort on an array of capacity 2, which then calls insertion sort on an array of capacity 1. But an array of capacity 1 is already sorted, so it returns back to the call when the second argument was 2. We then call insert array 2, which places the second entry into the appropriate location to sort the first 2 entries. Now the first 2 entries are sorted, so we're back to the call when the second argument is 3. We insert the third argument into the first 2 entries, which are now sorted, and now once that insert call returns, then the first 3 entries are sorted, so we now return again. And we're back to the call when the second argument is 4. We call insert on that array with the second argument being 4, and that places the 4th entry into the appropriate location to sort it, assuming, of course, that the first 3 entries are already sorted, which they are, and that sorts the entire array. Now let's look at a new example, something we haven't done in this class before because it's actually rather difficult. Let's print a number that in binary. Now, suppose we have a local variable that is storing the value 13. We know that 13 in binary is 1101. Now, it's easy enough to print out the least significant digit, 1, by simply calculating n modulo 2. That is the remainder when n is divided by 2. Now, but before we can print that last one, we have to first print the first 3 bits, 110. Now, how do we get 110? Well, recall that integer division discards the fractional part. So if a local variable stored the value 1101 or 13 and we divide that local variable by 2, then the result will be 110 and the fractional part of the division will be thrown out. And you will see that this is correct. 13 divided by 2 is 6.5, but 6.5 is not an integer, and therefore we discard the fractional component, which is 6, and therefore the result is 110, which is the binary representation of 6. Thus, in order to print 1101, we must first print the first 3 bits and then print the final 1. But to print 110, we must first print the first 2 bits and then print the 0. To print the 2 bits 1, we must first print the first bit 1 and then we can print the second 1, which we found again using modulo. And to print a single bit 1, well, we just print that bit. That sounds like a recursive algorithm. Now, as with the 2 previous functions that we implemented recursively, this one is also reasonably straightforward. So here we see our function body. First, we deal with the base case. In this case, the base case is when n is only a single bit, and that is when n is equal to either 0 or 1. In either case, we just print out n, and that will result in either 0 or 1 being printed to the screen. However, suppose n is greater than 1. In that case, we will have to print it recursively, as there is at least 2 bits in such a number. So the first step we will do is we will call the function recursively on n divided by 2. Now, why is that? Well, suppose, for example, we were calling print binary on 42, which is 10, 10, 10 in binary. So the first thing we do is we recursively call print binary on 42 divided by 2, or 21. Once that is complete, then we will print the last bit of 42, which can be found by calculating n modulo 2. So in this case, that will print 0 to the screen. All right, so this is a perfectly acceptable recursive implementation of printing a binary number, or a number in binary. Now, to test this implementation, we could author the following program. So in this program, we are simply going to print in binary every single number between 0 and 17. Now, if we run this program, we get an output equal to what we expect. Let's now rewrite this to print negative numbers. So the for loop goes from 0 to 17 inclusive, but now we will print negative k. So we will print 0, then negative 1, then negative 2, and so on. Let's take a look at the output. Oh wait, that doesn't look like binary. Well, except for the first two. Well, we have 10 and 11 there, but I don't think those are the binary representations. These all look like decimal. So, what was the problem? Why does this fail? Well, very quickly you notice that we have the condition n less than or equal to 1. Well, if n is less than or equal to 1, well, negative 10 is less than or equal to 1, then this just prints out that number. And negative 10, when printed to the screen, appears as negative 10. We can correct this by replacing the condition as we will print a number if and only if it is equal to 0 or 1. So now negative numbers that are greater than negative 1 will fall into the second case. All right, let's try that out. Now, when you see this output, the first thing you should be asking yourself is, why are we seeing a negative 1 being printed? After all, the only thing our function ever prints is 0 or 1 in the base case, or n modulo 2 in the recursive case. Well, you may not recall from a while back, we actually indicated that n modulo 2 is that number such that this equation is always true. So n is always equal to 2 times n divided by 2 plus the necessary remainder to bring us back to n. So, for example, 7 divided by 2 in integer division is 3. But 7 is equal to 2 times 3 plus 1, and therefore the remainder, when we calculate 7 modulo 2, that must be 1. 6 divided by 2 is 3, and 6 is equal to 2 times 3 plus 0. The remainder is consequently 0. Now, negative 6 divided by 2 is negative 3. Negative 6 is indeed equal to 2 times negative 3, and therefore the remainder is 0. But negative 7 divided by 2, when we discard the fractional component, is negative 3. But 2 times negative 3 is negative 6, and to get us back to negative 7, we must subtract an additional 1 off of negative 6, and therefore the remainder is now a negative number. Okay, so we have to now potentially deal with negative remainders. That sounds a little bit frustrating. Isn't there an easier way to print negative 13? Well, the most reasonable format for printing negative 13 would be to have negative 1101. Well, the easiest way to do this is to print a minus sign and then print positive 13, because we know our function already works for positive integers. Consequently, we now have one additional case. So we start by checking. If n is less than 0, we print out a negative sign, and then we call print binary, the same function, on negative n. All right, so if the parameter n has the value -13, we're in this first case, we print out the minus sign, and now we call print binary on +13. Well, now we are in either the second or the third conditions of this cascading conditional statement. Now, we've already discussed this previously, that when you're testing your code, you should always test for all of the edge cases. Here's an interesting edge case which you may not have thought about. Let's try printing -2 to the 31, which is the number we see here. That is the largest possible negative integer. So that should actually print as -1 followed by 31 zeros. That's what it should print like. But if you go and test this with our previous function, the output's actually going to be a little bit interesting. Either nothing is going to be printed and your program crashes, or you're going to see a lot of negative signs printed and then your program crashes. No digits are ever printed. You don't have to investigate this if you don't want to, but I'd suggest you try to look into it and talk about it with your friends. As our next example, we're going to implement the binary search algorithm as a recursive function. Now, the binary search takes an array with a given capacity and searches for a specific value, and the behavior, as you may recall, is as follows. If the value is found in the array, the index where it was found will be returned. So this is going to be an index between 0 and capacity -1. If the value is not found in the array, then capacity is returned. So this is how we will determine whether or not the value is found in the array. Is it equal to capacity? No. Is it less than capacity? Yes. And I can say less than because standard size t is an unsigned integer type. Let us first begin by describing the binary search recursively. For simplicity, we're going to have the base case as follows. If the array has a capacity of 2 or less, essentially this means that all we have to do is check the existing entries to see if our value is there, and if so, return the appropriate index, otherwise return the capacity. If the capacity is 3 or greater, and let's look at the example below, then we're going to check the middle entry. Now, if the middle entry equals the value we're searching for, we're going to return its index. If the middle index is greater than the value, we'll recurse on the array up until, but not including, the middle entry. And finally, if the middle entry is less than the value we're searching for, we'll recurse on the array starting at the next entry following the middle entry up until the end. Okay, this sounds like a perfectly good recursive algorithm because in either of these two cases, we will be performing a binary search on a smaller array. In fact, an array that is approximately half the size of the original array. Now, implementing the base case is actually quite easy. For if the capacity is less than or equal to 2, then we're just going to have a for loop that starts at 0 and goes up until and including capacity -1. And this works whether or not capacity is 0, 1, or 2. If we find the value in any of these array entries, then we return the corresponding index. Otherwise, if the loop finishes, we obviously haven't found the value, and therefore we just return capacity. This is almost like a very limited linear search. Next, let's find and check the middle entry. Now, in this case, the easiest way to find the middle entry is just to divide the capacity by 2. So we'll perform that calculation and assign it to a local variable middle index. Thus, the first step we do is check, is what is located at this middle index equal to the value we're searching for? If yes, we're just going to return the middle index. Now the question is, how are we going to recurse if the entry at the middle index is not equal to the value we're searching for? In any such case, it always makes sense to look at a concrete example. So in this case, let's just arbitrarily pick this array which has capacity 9. Now, we can calculate the middle index by just calculating capacity divided by 2. 9 divided by 2 in integer arithmetic is 4, and so the middle index is here. So assume that the value we're searching for is not equal to 7. Well, suppose that we find that the value we're searching for is less than the entry at middle index. Well, to search this array from entries 0 to 3, the appropriate function call or recursive call would be to have the capacity be middle index, which is 4. So this would search entries from 0 to middle index minus 1. All right, that's reasonable. So suppose we're searching for the entry 3.7. Now, the call that we see here is going to return the index 1 because that's where 3.7 is found. Well, that's okay because 3.7 is also in the index 1 of the array of capacity 9. So that would in fact be the appropriate value to return. Now, suppose instead we were searching for the entry 4.6. Well, 4.6 is not in that array from 0 to 3. So in that case, this particular function call would return the value middle index, which in this case is 4, because that is the capacity of the array we are searching on. But wait a second. If we are now going to say that 4.6 is not in this array of index of capacity 9, we actually have to return 9, not 4. All right, so if the value we're searching for is less than the entry in the middle of the array, we will begin by calling binary search recursively, where the implied capacity of the array is now middle index. So this will search the array from indices 0 to the current value of middle index minus 1. That is, it will search the first half of the array. Now, we will take whatever value is returned by this and assign it to the local variable returned index. We will now check, is the returned index equal to the middle index? Well, if so, this means that the value was not found in the first half of the array, and therefore it's not in the array with the given capacity. So we will return capacity to flag that it's not in this larger array either. Alternatively, if the value returned was between 0 and middle index minus 1, that means the value actually was found in one of those first entries. Therefore, we will just return whichever index was returned by the recursive call to binary search. Now, suppose the opposite. Let us assume that what is at the middle index is less than the value we're searching for. In this case, we want to search recursively the second half of the array. Now, the first entry of the second half is at, in this case, 5. Or, alternatively, we can calculate it as being middle index plus 1. The capacity of this second half of the array is 4. That is, it's the original capacity 9 minus the middle index, which is 4, minus 1. Now, what is the address of the entry at index 5? Well, we can calculate this one of two ways. So we can ask, what is the address of the array entry 5? Alternatively, of course, we should more generally ask, what is the address of array entry middle index plus 1? Because after all, we want to know what is the address of the entry immediately following the middle index. Now, if you recall pointer arithmetic, you will also recall that we can calculate that address by just adding 5 onto array, because when pointer arithmetic occurs, it doesn't just add 5 onto the address, it adds 5 times the size of each entry of the array. So if this is an array of double, it would actually add 5 times 8 onto the address of the array itself. So we could alternatively, and just as correctly, calculate array plus 5, or more generally, array plus middle index plus 1. Therefore, the appropriate call is to recursively call binary search on array plus middle index plus 1, so starting at the entry after the middle index. The capacity of this new array will be capacity minus middle index minus 1, and we are still searching for the specific value. Okay, suppose we make this recursive call to binary search that searches the second half of the array. It looks a little bit convoluted, but again, we saw in the previous page that this searches the entries from 5 until 8. However, it's a recursive call. So what do we do with returned index? Because now it's going to return a value, at least in this case, between 0 and 4. Suppose we're searching for the entry 10.9. Now, 10.9 in the smaller array is at index 2, so the recursive call to binary search would return the value 2. But we want to return the value 7 because it's in the 7th index of the larger array. So therefore, we will be returning 2 plus middle index plus 1. Now, suppose instead we were searching for the entry 12.4. 12.4 is not in the larger array, and therefore it's not in the smaller array, and therefore it will indicate or flag that it was not found. If it was not found, it will return the capacity of the array that was being searched. So in this case, it will return the capacity of 4, as that is the capacity of the smaller array. However, we also want to now return a value indicating that it is not in the larger array of capacity 9. So we should actually be returning the capacity 9. Well, if we note this, we see that 9 is equal to 4 plus middle index plus 1. So whether or not the value was found or not found, in either case, we just take what was returned and add to that middle index plus 1. Thus, The complementary alternative body of this cascading conditional statement is the situation when the array middle index entry is less than the value we're searching for. Therefore, we will make the appropriate search of the right hand of the, or right half of the array past the middle index, and whatever value is returned, we will add to that middle index plus 1. Okay. Consequently, this is our recursive implementation of the binary search algorithm. Now, whether or not this is easier to understand or more complex to understand than the iterative searching technique we saw before is questionable. I think this one's easier to understand, but the previous one actually does use significantly less memory as it is not recursive. In either case, both of these algorithms work correctly, and you'll notice that with this case, we didn't have to deal with any special cases. This is the correctly functioning binary search algorithm. Now, for our next example, we need a little bit of a setup. Consider the numbers 1, 2, and 3. Now, if I was to choose one from these three, or two from these three, or all three from these three, or none from these three, I get all possible subsets. So in this case, I have none of them, one of each, two different ones, and all three. As you may recall from secondary school, the number of possibilities for each of these is 3 choose 0, which is equal to 1, 3 choose 1, which is equal to 3, 3 choose 2, which is also equal to 3, and 3 choose 3, which again is equal to 1. I'd like a program that prints these out. Now, we don't care about the order. We just want all of these entries, all these possible combinations to be printed out. Similarly, given the set 1, 2, 3, 4, again, all possible subsets include all these possibilities here. And if you count these, you will notice that there are 2 to the 4 possible subsets. Why? Because for each of the 4 entries, we may choose or not choose to include it. Consequently, there's 2 to the 4 possibilities of choosing or not choosing each of the entries. Once again, we see that the number of possibilities equals 4 choose none, 4 choose 1, 4 choose 2, which is equal to 6, 4 choose 3, and 4 choose 4. For this, once again, we would like some sort of output that has all of these cases. Now you're wondering, why do we care? Why would a computer or electrical engineer care about possible subsets? Well, these may represent possible inputs or combinations of inputs, in which case you'd like to test those that are possible. As one last case, as we go up, now all possible subsets of the set 1, 2, 3, 4, and 5 include the 2 to the 5 possibilities listed here, and we'd like to have an output that displays all of these. Now, how are we going to print all subsets of the set 1 through n? If n was fixed, you could actually just have a whole bunch of for loops, but we don't know what n is. So this sounds like it may be something appropriate for recursion. Let's assume that we have an array of n Boolean values. And if the kth entry of this array is true, then we will assume k is in the subset. Otherwise, k is not in the subset. Consequently, every single different array with different entries of true and false represents a different subset. If all of the entries of the array are false, it represents the set containing no entries, whereas if all of the entries of the array are true, then it represents the set containing all n entries. We could therefore, given any state of the array, print all the values. So here we see a for loop which loops from the index k being 0 all the way up until n minus 1. And if the kth index is true, then we will print k plus 1, because after all, the first entry is at index 0, the second entry is at index 1, and so on and so forth. And for this specific problem, we've asked for the subsets of the set 1 through n, not 0 through n minus 1, so we have to make an appropriate accommodation. So, for example, suppose our membership array was the following. Here indices 0, 3, 4, and 7 are true, and therefore this represents the first, fourth, fifth, and eighth entries. Therefore, if we were to print this out, we would see an output as follows. This represents the subset of entries 1, 4, 5, and 8 of the set 1 through 8. Now, how are we going to print all subsets of the set 1 through n? If n was fixed, you could actually just have a whole bunch of for loops, but we don't know what n is. So this sounds like it may be something appropriate for recursion. Let's assume that we have an array of n Boolean values. And if the kth entry of this array is true, then we will assume k is in the subset. Otherwise, k is not in the subset. Consequently, every single different array with different entries of true and false represents a different subset. If all of the entries of the array are false, it represents the set containing no entries, whereas if all of the entries of the array are true, then it represents the set containing all n entries. We could therefore, given any state of the array, print all the values. So here we see a for loop which loops from the index k being 0 all the way up until n minus 1. And if the kth index is true, then we will print k plus 1, because after all, the first entry is at index 0, the second entry is at index 1, and so on and so forth. And for this specific problem, we've asked for the subsets of the set 1 through n, not 0 through n minus 1, so we have to make an appropriate accommodation. So, for example, suppose our membership array was the following. Here indices 0, 3, 4, and 7 are true, and therefore this represents the first, fourth, fifth, and eighth entries. Therefore, if we were to print this out, we would see an output as follows. This represents the subset of entries 1, 4, 5, and 8 of the set 1 through 8. Now, how are we going to print all subsets of the set 1 through n? If n was fixed, you could actually just have a whole bunch of for loops, but we don't know what n is. So this sounds like it may be something appropriate for recursion. Let's assume that we have an array of n Boolean values. And if the kth entry of this array is true, then we will assume k is in the subset. Otherwise, k is not in the subset. Consequently, every single different array with different entries of true and false represents a different subset. If all of the entries of the array are false, it represents the set containing no entries, whereas if all of the entries of the array are true, then it represents the set containing all n entries. We could therefore, given any state of the array, print all the values. So here we see a for loop which loops from the index k being 0 all the way up until n minus 1. And if the kth index is true, then we will print k plus 1, because after all, the first entry is at index 0, the second entry is at index 1, and so on and so forth. And for this specific problem, we've asked for the subsets of the set 1 through n, not 0 through n minus 1, so we have to make an appropriate accommodation. So, for example, suppose our membership array was the following. Here indices 0, 3, 4, and 7 are true, and therefore this represents the first, fourth, fifth, and eighth entries. Therefore, if we were to print this out, we would see an output as follows. This represents the subset of entries 1, 4, 5, and 8 of the set 1 through 8. Thus, we could implement this function of printing subsets as follows. Here we see the function definition with the body, and now we'll deal with a default or base case. The base case is when we've assigned a value to each entry of the array, and so consequently the third argument will be equal to capacity. So in this case, we just go from 0 to capacity minus 1, and if that entry of the array is true, we shall print out the value k plus 1. This is again because the indices go from 0 to capacity minus 1, but we actually want it to print values from 1 to capacity. So once we have listed all of the current entries with membership in this set, then we print an end-of-line character so we can continue printing the next set. Now the complementary statement includes first indicating, oh, the membership of the current index is going to be true. So at this point we're assuming that when we recursively call, then this entry at current index will be displayed to the screen, specifically current index plus 1. So that's in the set. So now we will recursively call print subsets. Next, we'll indicate that the current index entry is not to be printed, and once again we will recursively call print subsets on everything that is left. Nice. Now, a little bit beyond the scope of this course, so don't worry about this too much, but there's something here that we should do to make life easier for the user. We shouldn't require the user to create an array of Boolean values and then pass it in appropriately. Instead, the user should not have to do anything else other than call this function here. So I now have a print subsets function, but it only takes one parameter, and that is an unsigned integer n, meaning we want to print all subsets of the numbers from 1 to n. Now here I am using an unsigned int because I'm trying to explain that this is a mathematical algorithm meant to print subsets. It's not meant to deal with the implementation of this function in C++, which of course uses an array. However, inside this function now, we will create a local array of capacity n of Boolean values, and then we will call print subsets, but now with that array as the first argument, its capacity n as the second argument, and the current index being 0. This will then proceed to print all of the subsets of the integers 1 through n. Thus, a test for this recursive function may be as follows. Here I have a main function where k goes from 0 up until and including 10. I then just print some sort of demarcation line to indicate these are the subsets from 1 to k, and then I call print subsets with the argument k. Now notice that there is indeed one subset of nothing, and that is nothing. So this should print 1 for k equaling 0, 2 subsets for k is equal to 1, and so on and so forth. And this does. Okay, so now we've implemented the all subsets function. We'll now see where this is actually possibly useful in simulating and testing your designs as both electrical and computer engineers. Now here's an example which actually uses the previous example. Now on a motherboard, or any circuit board in general, you can have pairs of jumper pins that can be optionally connected with a jumper in order to configure the operation of the circuit board. So a circuit board may have n pairs of jumper pins. Each pair can be either open or physically shorted by adding a jumper. So for example, here we see that we already have 2 jumpers in place, and we could short the second last pair by pushing a jumper down. All right. Now, suppose you are providing or selling a circuit board in your product, and this product is being made available to consumers. Now, your particular application using the circuit board may require that certain pairs of jumpers must be opened and other pairs must be closed, but there are additional pairs of jumper pins that may optionally be open or shorted by the user of the product for additional configurations. So for example, here, pairs 1, 4, 8, 10, 11, and 15 must be shorted, while pairs 0, 2, 3, 5, 9, and 13 must be left open. This leaves pairs 6, 7, 12, and 14, which are user configurable. That means the user can optionally leave them open or shorted to suit their purposes. Now, if you have software that uses this circuit, you must test your software under all possible user configurations. So what we're going to do is we will let 0 represent a pair that must be open, 1 representing a pair that must be closed, and a question mark is used to represent any pair that is user configurable. So for the above situation, we would represent this as this sequence of 1s, 0s, and question marks. Well, this is a string with an alphabet of 3 possible characters. Thus, as stated, we must test our software against all possible user configurations, and for the previous one, we would have the following string representing the configurations. There are 4 question marks, therefore there are 2 to the 4 possible configurations. All possible configurations are shown here. In the first one, all of the 4 user selectable pins are open, whereas in the last one, bottom right, all of the user configurable pairs are shorted. Your goal is to author a recursive function print configurations which will take a C-style string, that is a null character terminated string, as an argument, and the characters in that should be either assumed or you can check to be only 0, 1, or a question mark. Your function will print out all possible user configurations, and as a comment, you may modify the string before you pass it on recursively. So, for example, the following program here should have an output that matches all of the entries or possibilities shown on the previous slide. So there are 16 pins. Because it is a C-style string, that means that we need to allocate memory for 17 entries in that character array, and then we pass it on to print configurations. The output should be all possible values seen on the previous slide, but the order doesn't matter. However you do it is up to you. All right. Suppose you had 2 piles of sorted cards. You know that in each pile, 1 is the smallest because it appears on top, or in the second case, 7 is the smallest as it is the value that appears on top. How could you create a single pile of sorted cards? Well, what you do is you take 1 and then you'd look at what's left. There's 4 and 7. Well, 4 is the next smallest value, so we would take 4 as well, and we put that behind 1. Now, between 7 and 12, I would take 7 next, and between 12 and 14, I would take 12. Then I would take 14 from the right pile. Then I'd keep taking 17 from the right pile, 21 from the left pile, 23 from the right pile, 25 from the right pile, 30 from the right pile, then 31 and 34 from the left pile, then 42, 47. Oh, and there's nothing left in the second pile, so I can just take whatever's left in the first pile and append it to the end. That's exactly what you would do in the real world. Now, suppose we had 2 sorted arrays. Here, one is of capacity 10, the second is of capacity 8. And we'd like to merge these 2 into a single sorted array. What steps could we take? Well, let's have 3 indices. In the case of the 2 arrays, the index points to the next entry that has not yet been copied over, and the array in the middle, the index is that location where the next entry is to be copied to. So, looking between 1 and 7, we copy 1 down, and then we increment both that index and the other array's index. Now, comparing 4 and 7, again, we copy 4 down and increment those 2 indices. Comparing 12 and 7, we copy 7 up, and then we increment that index and the final array's index. Between 12 and 14, we copy down 12, increment those two indices. Comparing 21 and 14, we copy up 14, increment those two. 21 and 17, let's copy up 17, increment those indices. Copy down 21, increment those indices. Copy up 23, increment those two indices. Copy up 25, increment. Copy up 30, increment. Copy down 31, increment those two. Copy those 34, increment those two. Now we are copying up 41 and 47. And now the index to the second array equals its capacity, indicating that everything from that array has been copied over. Consequently, all we need now do is copy everything over from the first array. And we are done. So suppose now instead we have a single array where the first m entries are sorted and the second n entries are also sorted, but the entire array is not sorted. How could we create a single array of capacity m plus n that contains a sorted list merging these two sorted arrays? Well, easy enough. As before, we would have indices pointing to each of the appropriate entries. The smallest entry in the first array, the smallest entry at the second half of it, and the location in the new array to which we will copy the next smallest entry. And then, as before, we proceed as follows. We copy down 1 and then 4. Then we copy over 7 and 12, 14 and 17. From the first half we copy over 21. From the second half we copy over 23 and then 25 and 30. From the first half we copy over 31, 34. Then we copy from the second half 42, 47. And now the index is beyond the end of the first array, second half of the array, and so we simply copy over the remaining entries from the first half of the array. And now we are finished. We have created a single sorted list from an array that was previously split into two sorted lists. Now here's the implementation of merging such an array where the first half is sorted and the second half is sorted, and we'd like to merge it into a single array that is sorted. Now this is important. This is a little bit beyond the scope of this course, so just enjoy it or skip it as you wish. The first thing we're going to make sure is that the first half is sorted and the second half is sorted. So the capacity of the entire array is cap1 plus cap2. The first cap1 entries are sorted and the second cap2 entries are also sorted. So what we will do is we will create a temporary array of capacity cap1 plus cap2. We will then have two indices that point to the current smallest entry in both the first half and the second half of the array, calling these K1 and K2 respectively, and then the location in the temporary array to which we will copy the next smallest entry, and we will call this J. Now, while the first index is within the range of the first half of the array that's sorted and the second index is within the range of the second half of the array that is sorted, we will find the smaller of the two entries and copy it over to the temporary array at location j. If we copy from array the first half, we increment k1. If we copy from the second half, we increment k2. In both cases, we increment the index into the temporary array. Now, this while loop will halt as soon as one of the two indices is beyond the corresponding entries of that array. After this, we copy over any remaining entries in the first half of the array to the temporary array. And notice that if k1 is already beyond the first half of the array, this loop doesn't run at all. And this copies over all the entries from the second half that are left over into the temporary array. Having done so, we have now a sorted temporary array, and so we will copy all of the entries back to the array starting at 0 and going up until cap1 plus cap2 minus 1. Alright, and if we wanted to check to make sure, we could assert that the array of capacity cap1 plus cap2 is indeed sorted. Now here is what is likely the simplest recursive sorting algorithm out there. If an array has only 0 or 1 entries in it, it's sorted, so return. That's the base case. Otherwise, divide the array into two, sort each of them recursively using merge sort, and then merge the results. All right, well, let's implement that. So here is our function body. Here's the base case. If the capacity is less than or equal to 1, we just return. Otherwise, here's the alternative body. This is the recursive case. In the recursive case, we will start by dividing the array into two. Capacity 1 is the first half of the array. Capacity 2 is whatever is left over. We will then call merge sort first on the first half and then call merge sort on the second half. Assuming that these work, following this, both the first and second halves of the array should be sorted. At this point, all we have to do is call merge on that array with those two given capacities. That's it. A very elegant and simple algorithm, and one that is reasonably fast. Indeed, in your second year course, you will learn on algorithms and data structures, you will learn that this function is significantly faster than either insertion sort or selection sort. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!